This is where I left you at the end of part 1. Well, no one has yet succeeded in getting a living cell to happen using any mixture of materials and techniques. It is not for want of trying. There are thousands of articles written every year on the subject. This presentation is designed to show you just how difficult and unlikely it was for that first living cell to be formed. First, I will show you some of the complexity inside those so-called simple cell walls, then discuss the reason the chemical process of making RNA or DNA cannot happen in a pure aqueous environment. The latest research indicates that clay surfaces can act as the critical catalyst, helping organize random organic molecules into these basic genetic units for living processes to begin. Catalysts help chemical reactions happen much more efficiently, but also need life's universal energy source called ATP. Finally, I will review all the things that our moon has done for life to exist on our planet. This slide is to remind you of the minimal qualities necessary to define life. In other words, a living cell must be able to reproduce itself. It must be able to use energy to perform its functions. It must be able to change over time. It must be able to grow and develop. It must maintain homeostasis. It must be able to respond to the environment and evolve. And it must have an internal genetic code that it can use to reproduce itself and make proteins. Before we talk about how the origin and continued presence of the moon allowed living cells to form and thrive, I'm going to have a brief diversion to emphasize just how complicated a living cell is, and also how living cells can balance the entropy law. That is, progressive time develops less organization or more entropy. This fuzzy ball of over 1 million stars hides an infinite complexity which we overlook when we admire it in a telescope. It is easy to forget just how complex the processes are in a living cell when we hear that any place with water will automatically develop living cells. In the next slides, I will give you some examples to consider. These are some of my favorite cellular devices which must be present for any cell to work. If the dynein on the left were 6 feet tall, the cell would be 30 miles across, and it would have to carry its protein package 10 miles or so on special roadways within 15 minutes, or the cell would take it apart. The ribosome on the right reads messages from the DNA in the nucleus and makes needed protein, one of 20,000 or so, which the dynein then transports. Here's another example. Nerves function by passing protein chemicals between their dendrites. These are produced and carried by dyneins to make vesicles which are excreted on demand. The ubiquitous green-colored roadways make up as much as 20% of a cell's material. This complex process obviously needs more than a simple body of water to be created. But this is literally the mother of all complex proteins. Before the chlorophyll complex was developed, living cells had to rely on very slow, inefficient, non-oxidative processes to use the sun's energy. It took about 1 billion years for this complex invention to occur, and it followed with a 17-power jump in efficiency and a sudden profusion in numbers and complexity of life, forming the oxygen atmosphere we enjoy today. The first photosynthesizing cells were very small cyanobacteria, which were engulfed by larger anaerobic bacteria, and their genome joined to become a supercell. This dramatic transition likely could happen only because of the long, stable, nurturing environment created by our moon. There is an odd counterintuitive quality about the formation of an extraordinarily complex living cell when the average entropy, which equals chaos and disorganization, across the universe is increasing. However, it turns out that computer analysis of the amount of entropy increase if sunlight plays on inert seawater versus the increase when the sunlight plays on water teeming with organic life seems to verify that more energy is lost back into space in the latter scenario. I recommend you watch my Big Bang presentation for more information on entropy and the universe and a lot of other neat ideas. Creating ribonucleic acid is the minimal first step before there can be any hope of living cells developing. The nucleobases can form without too much problem under many environmental scenarios, but the ribose molecule responsible for holding them in a long chain is another matter. Ribose can only be formed and linked into chains by a specific reaction sequence on a dry surface or a catalyst such as clay. A tidal zone in a temperate climate, warm to cold conditions, is ideal. Dilute solutions of the reactants can be concentrated in this condition in tidal pools and brought together on a sticky clay surface to join. This very complex reaction needs energy to go forward. New studies suggest that ATP was the likely source of this energy. It is fairly easy to form from organic molecules originally available, and is still the essential power supply for all cell processes. So this is ATP, the energy battery which powers all cell processes. It is theorized that ATP may have formed first energized by sunlight and then incorporated into protocells, and then complex life formed as a way to allow the ATP energy to be dispersed, that is, increase in entropy. And this would explain how ATP became the cell's powerhouse coming from primordial oceans. It is relatively easily formed from organic soup plus sunlight. This slide pictures a demonstration of what happens after a random string of RNA is mixed with a solution of amino acids in the presence of ATP. This would be likely the situation present in a tidal pool. It immediately starts making long strings of proteins. In this case, RNA has to catalyze its own reaction. In a modern cell, there are complex proteins which more efficiently do the catalysis, but these needed millions of years to be developed in the first living cells. So the process on this slide solves a chicken and egg problem which has been contested in the origin of life discussions. I must emphasize again, this process also requires a temperate climate zone, tides, clay, billions of tidal pools, and hundreds of millions of years before random processes eventually led to functional results. This slide illustrates how a clay substrate takes the random molecules out of solution and holds them within billionths of a centimeter of each other so they can react to make RNA. The point here is that the bases that make up the RNA molecule, adenine, cytosine, guanine, and thymine, are too dilute in an open aqueous solution to have any hope of making significantly complex RNA molecules that could be a precursor to living cells. The remaining difficult step, illustrated here, is making an enclosure for the RNA and amino acids so any useful products don't drift away. The best solution seems to be a film of lipid material floating on a tidal pool. Experimentally, this readily disperses into tiny cell-sized bubbles when agitated. If there is RNA and amino acids in the solution, some of them are enclosed in the bubbles. Under the right circumstances, the bubbles link together into long strings, which can split when they get too long, much resembling normal cell division. So before we got to the formation of this handsome mammal, there were a whole lot of things that had to happen with the help of our moon. This is the beginning of a summary of just what the moon did for us. First of all, it added mass to the proto-Earth. It allowed us to have a critical layer of post-perovskite, allowing efficient convection and volcanism. It allowed land creation from volcanism and plate tectonics, and the volcanism added nutrients to the soil. Volcanism also adjusted the atmosphere, helped with heat retention and saving us from permanent ice age. And also plate tectonics and CO2 carbonate cycle prevents runaway greenhouse effect like Venus. Next, I want you to remember the effect of the donated spin and tilt, which helped create our core dynamo, and the Coriolis effect on the core, along with the protective magnetic field. Also, the Coriolis effect on atmosphere and water, distributing heat vapor from the tropics, winds and rain, making life habitable. Next, I remind you of the effect of our axial tilt, creating seasons critical to development and wide distribution of higher organisms. Without changing sun exposure, the weather would be very static, with extreme heat at the equator and extreme cold at the poles, with likely permanent glaciation of most of the land. The moon also gave the Earth stability. Without the stability, the axial tilt and weather would be unstable like Mars, with relatively rapid changes which would discourage survival of most higher organisms. Finally, we have the extremely important tides and waves, which were originally 600 feet high. They helped break down the shoreline and create soil and blend essential metallic elements into the soil worldwide. They created microenvironments for life to develop and thrive, extending far inland with billions of reaction pots and clays for reactive surfaces. The tides mixed atmospheric and soil nutrients into the water. The sloshing of the waves helped bring excess CO2 back into solution to prevent runaway greenhouse effect. Now I'd like to consider poor little Mars, only a fraction of Earth's size. In order for life to develop on Mars, it would have needed a stable climate for 1 billion years. Unfortunately, Mars was too small to keep volatiles for long. Mars had no plate tectonics, so it did not have the ongoing volcanism and stable water source. It also, without a moon, had an unstable axial tilt with severe climate changes. Without water, of course, and without a moon, there was no source of waves, tides to make soil and mix organics into the water and bring seawater onto the land where chemical reactions occur. The water that was on the moon was shallow, and there was no tectonic activity. Also, there was no magnetic shield to protect organics and atmosphere from solar radiation. It also had no deep oceans to stabilize climate and protect life, and a number of other things. So I'm sorry to disappoint you about Mars. Well, I'm as excited as everyone else about the Europa Clipper mission coming up, but I'm afraid that Europa has even dimmer prospects for life, even though the public media would have it otherwise. There is no external source of energy other than gravitational friction from Jupiter. There is no way to get high concentrations of nucleotides or amino acids next to each other to react. Nevertheless, I'm sure the mission will be full of amazing surprises and scientific advancement. I hope you are convinced that Earth is at least unique in our solar system, if not the galaxy, because of its special moon and orbital dynamics. Frank Drake, in 1961, wrote an equation to calculate the chance of intelligent life in the universe. He did not have enough information at that time to include the presence of a large moon. Today, I think he would agree that the search for intelligent life should include a search for a planet which includes a wobble from the gravity of a nearby moon. Thank you for your attention. Let me know what you think.